Welcome. Let's start. So today the plan is we want to wrap up dynamic programming and talk about linear programming. So we've seen quite a few examples of dynamic programming. So one thing we could do is just skip to linear programming, but there is one really beautiful application of dynamic programming, which we just can't miss. So I'm just going to show it to you. So we'll do this quick example of dynamic programming quickly, and then we'll start talking about an entirely new topic, linear programming. So what is the problem? This is a very familiar problem to all of you. So it's the all pair shortest paths problem. So you're given a graph with edge weights. So these edge weights can be positive or negative. And your goal is to compute the shortest paths or distance between every pair of vertices in the graph. Positive or negative without negative cycles for now. Okay? And this is your goal. And, what is a naive strategy would be to run Dijkstra, assuming you have positive edge weights. Even if you had positive edge weights, you could run Dijkstra from every node, starting from every node I, right? So then you'd have, n different Dijkstras, or suppose let me just say the size of the vertex set is n. So you have n vertices. And so then you have n Dijkstra's algorithm. So the runtime would be coordinate of v times the runtime of Dijkstra, which is e log v. Okay, so that's v e log v. Okay. So you want to compute shortest paths between every pair. So Dijkstra lets you compute shortest paths from a given vertex. Now you want to compute between every pair, so that's why it takes you this much time. Okay, so now what we'll do is we'll see a very nice algorithm based on dynamic programming for this problem, which basically runs in time n cube, order n cube, which will be, which is better than Dijkstra for some parameters. But it's just something new, so let's just dig in. Okay, the problem is again very familiar. It's just the shortest paths. You're given a graph, and you want to compute shortest paths or distances between every pair of node in the graph, all the n squared pairs of distances. Okay? Is the question clear? Just the good old shortest path between every pair. Okay, let's see. Okay, so we want to solve it using dynamic programming. So we have to come up with subproblems. So I'm just going to tell you the subproblem which we'll use here. It's a little bit, too clever, but so it has parameters d, a vertex I to a vertex j. So you want to find the distance from I to j. That makes sense. And then it has a third parameter, which is k. Okay, and think of k as 1 through k. Okay. So what is Dijk? This is the shortest path from, actually I should say length of the shortest path from I to j all of whose intermediate vertices are from 1 through k, which only uses 1 through k as intermediate vertices. Meaning the subproblem is asking for the shortest path from I to j, such that if I look at all the vertices here, they come from just 1 through k. They all are from the set 1 through k. Just for example, what is dij0? Okay, what is dij0? It's the length of the shortest path from I to j that uses only intermediate vertices from 1 through 0, which is the empty set. So this is the length of the shortest path with no intermediate vertices. Right, that's what the definition is saying. dij0 is the length of the shortest path with no intermediate vertices. So, and we know what this is, right? It's going to be the length of the edge ij. Because if you're not allowed to use any vertex as an intermediate vertex, dij0 is just the length of the edge wij. wij. So, what is dijn? Okay, as I said, we want to think, what is dijn? It's the length of the shortest path from I to j that can use any intermediate vertex from 1 through n. All of its intermediate vertices are from 1 through n, which is all the vertices. So this is just the length of the shortest path. dijn is just the length of the shortest path. From I to j. Right? And so if I look at any dijk, it's the length of the shortest path such that every vertex that you encounter in the middle is from 1 through k, is one of the first k vertices. Okay? It's a weird choice of subproblem. Right? It's trying to do something really clever. You'll see when I write the recurrence, it will have a very simple recurrence relation. That's why we are picking this choice of subproblem. Any questions on this? This is definition of the subproblem clear? It's really important to sort of internalize the definition, so if you remember it without having to look at it. So dijk is the length of the shortest path from I to j that only uses vertices from 1 through k in between. Okay? Remember the definition because that's going to be important as we write the recurrence relation. All right? Okay, so let's see let's try to write a recurrence relation and see how it goes. So I want to know what dijk is. Okay, so what is dijk? Okay, so what is it? Well, it's the shortest path from I to j such that all the intermediate vertices, all these guys in the middle, are from 1 through k. Okay? Now, there are two cases. Either the vertex k is on the shortest path or not on the shortest path. Right? The vertex k can be one of two things. It can be on the shortest path or not on the shortest path. Okay? So let's sort of split it into two cases. Okay, so let's say k is on the shortest path. Actually, let's do the easier case. Suppose k is not on the shortest path from I to j. Okay, k is not on the shortest path. Well, k is not on this on the shortest path from I to j, which uses vertices from 1 through k. Okay, so we only allowed the path to use vertices from 1 through k as intermediate, and it's decided to not use the vertex k, which means the only intermediate vertices are 1 through k minus 1. Right? So if k is not on the shortest path, we only allowed the shortest path to use vertices from 1 through k as intermediates. We did not have k, so the only intermediate vertices are 1 through k minus 1. So every intermediate vertex every intermediate vertex is in 1 through k minus 1. Okay? So this path actually uses fewer choices for intermediate vertices. But we know what a shortest path from I to j that uses intermediate vertices from 1 through k minus 1 is. It is just d of I comma j comma k minus 1. Right? This would just be d of I comma j comma k minus 1. Okay? That is case 1. So if k is not on the shortest path, then what you have is d of I comma j comma k minus 1. Make sense? Okay, so now let's look at the other case. Okay, so the other case is you have so let me draw a line between the two cases. Okay, so what is the other case? You have the path I, and then this is the shortest path from I to j that uses vertices from 1 through k, and k is somewhere on the path. So k is part of the shortest path. So k is part of the shortest path from I to j using 1 through k. Okay? All right. So if k is part of this shortest path, if I look at the first section of the path, what can I say about that? That is clearly the shortest path from I to k. So this is clearly shortest path from I to k. And it only uses vertices from 1 through k minus 1 as the intermediaries. Because if I look at the intermediate vertices in this part of the path, right, the only intermediate vertices were 1 through k, and I'm telling you where k is. So if I look at the intermediate vertices, other intermediate vertices, they'll be from 1 through k minus 1. Okay? So all the other intermediate vertices will be from 1 through k minus 1. And so the shortest path from I to k that only uses 1 through k minus 1 is di comma k minus 1. And similarly, this part is d, it's the shortest path from k to j that only uses intermediate vertices from 1 through k minus 1. So let me write the recurrence again here. So what we got is this very simple, nice recurrence. Dijk is minimum of these two possibilities, is the minimum of, on the one hand, you can either be di comma j comma k minus 1, or you could be di k minus 1 plus d k j k minus 1. So the recurrence is saying dijk is the minimum of these two numbers. Okay, that's the recurrence relation. Okay? Yes, question? Okay, I'll answer that. Yeah, any other question? Okay, so the most important thing to remember as you try to understand this is the definition of Dijk. Dijk, now let's recall the definition again. It's the length of the shortest path from I to j, which only uses 1 through k as intermediate vertices. Okay? That's our subproblem, and that is a definition you need to remember very well. And so now, if I look at the path from I to j, that only uses 1 through k minus 1, 1 through k as the intermediates. So this path from I to j that I've drawn here is the shortest path from I to j that only uses 1 through k as intermediates. Okay? And now there are two cases. K is not in the shortest path, or k is in the shortest path. If k is in the shortest path from I to j, that he only uses 1 through k as intermediates. Now if I look at the first section of that path, it's a path from I to k, and it doesn't have k inside it because you'll never visit the same vertex twice along the shortest path. So the section from I to k is the shortest path from I to k that only uses vertices from 1 through k minus 1 as intermediates. So that's why it's di, k minus 1. Okay? And the second stretch is the shortest path from k to j that only uses vertices from 1 through k minus 1 as intermediates. So that's d of k, j, k minus 1. Okay, so all right. So the question is, should the second half from k to j be a single edge? We don't know where the vertex k is on this path from I to j. You're starting at k. Right. So that's why. So again, let's remember. Right. Let's read the definition very carefully because it's really important here. It's a very tricky definition. So it's not saying that it's using vertices, all the vertices from 1 through k. What it's saying is di, j, k is not the length of the shortest path from I to j that uses 1 through k as intermediates. It's the length of the shortest path from I to j, which is only allowed to use vertices from 1 through k as intermediates. So it might not use all the vertices from 1 through k. It might use only 3, or it might use all the vertices. We don't know. It's only allowed to use 1 through k. Right? It's maybe intuitively, if you want to think about it intuitively, you could say that you start with the graph, and you compute first you compute shortest paths where no intermediate vertex is allowed, which means from every vertex I, you need to just jump to j, and you incur the cost of the edge wij. And then you decide vertex 1, now you can be an intermediate. Okay, now paths can go through 1. You compute the shortest paths. Then you say vertex 1 and 2, now you can be intermediates. Paths can go through 1 and 2, and so on, so forth. So at any point you have allowed, at this point, you've allowed vertices from 1 through k as intermediates, meaning paths can go through them. They don't have to go through all of them, but they can use some subset of them, or they can go through them. And then you compute that. And then you get this recurrence relation, and you can see that. It's a very clever choice of subproblem that leads to a really simple recurrence relation and gives you a fairly efficient algorithm. In particular, this is the best algorithm we know for all pair shortest paths. Even today, it's been maybe 40 years now, and it has very simple pseudocode. I'm not even going to go into pseudocode. But the key thing about the recurrence relation you should realize is this recurrence relation. Usually, in many of our recurrence relations, thing on the left-hand side is minimum over many quantities on the right-hand side. Here, Dijk is a minimum of just 2 numbers. Going through the recurrence relation takes order 1 time. If I knew di, j, k minus 1, and these 2 other numbers, then computing the recurrence relation takes order 1 time, because I just need to add these 2 numbers and compare the 2 and output Dijk. So it's a very simple recurrence relation that leads to a very quick, very fast runtime. Okay? One last question, yes. Okay, so the question was about what to do if there is no path from I to j that does not use 1, that use 1 through k. I think that, for instance, di comma j comma 0, I said is wij, but maybe there's no edge from I to j. We can always assume there's an edge from I to j with cost infinity, and then we can work out the shortest paths, and you get the right answer. Okay, so I'll skip ahead to the next topic. I just wanted to show this clever reconciliation. You know, it's if you just stick to the definition and understand it, it's very simple, but it's very hard to come up with such a thing. Yeah, it's very nicely. Okay, let's move on to the next topic, I guess, the next big algorithmic hammer that we'll learn about, which is linear programming. Okay, linear programming. So, in short, a linear programming is an optimization procedure, right? It's a class of, it's a family of optimization problems. Right? How do they look? We'll see an example soon, but I just wanted to say in English how they look. Like, so it's like, you know, you have some variables, x1 through xn, some real valued variables, right? Some variables, which are real numbers. And then you have some maximize or minimize, some linear function of these variables, right? A degree 1 function of x1 through xn. And then you have some constraints, subject to some constraints, which are linear constraints. So you have a linear objective function you're trying to maximize or minimize with some linear constraints, and that's basically what a linear program is. Everything is linear. There's no degree 2 constraints. Everything is degree 1. That's a linear program. We'll see an example soon. The most important thing that you want to know about linear program, or the one bit of information that we want to give you, is that they can be solved efficiently. Right? It's a very powerful set of optimization problems that can be solved efficiently. You can download code from the internet or wherever, and there's lots of different algorithms to solve them in polynomial time and even faster. Okay? So it's widely used, efficiently solvable class of optimization problems. So let's see an example. So this is a really simple example, just a 2-dimensional one so that I can draw pictures. So you own a coffee shop, okay? And you can make 2 kinds of drinks, a cappuccino or a latte. And 1 unit of cappuccino takes 3 units of coffee and 1 unit of milk. Right? This is to make 1 unit of cappuccino, it takes you 3 units of coffee and 1 unit of milk. And to make 1 unit of a latte, it takes you 2 units of coffee and 4 units of milk. Okay? That's the situation. And what you have is you have 6 units of milk, so 6 units of coffee and 8 units of milk with you. Okay? And what you want to do? You want to maximize the number of, you want to make the maximum number of drinks. Okay? And so in particular, you have to decide how much of cappuccino you're going to make, how much of latte that you're going to make. And you have, this is your available coffee and milk and how much it takes to make 1 cappuccino and latte. So in particular, I mean, the thing that you need to decide, the 2 decision variables are, the 2 variables that you care about is x, let's say, x is the number of units of cappuccino, and y is the number of units of latte. All right? So you need to know, you want to know the value of x and y. And x and y are positive real numbers for now. So these are positive real numbers. Okay? Okay. Now, what are the constraints on x and y? Well, your resources place constraints on x and y. So if you make x units of cappuccino and y units of latte, right, you will consume, so you're making x units of cappuccino and y units of latte, right? You'll consume 3x plus 2y units of coffee. You will need 3x plus 2y units of coffee, right? This is how much coffee you need to make x units of cappuccino and y units of latte, right? And this has to be less than the total amount of coffee that you have, which is 6. So you get a constraint that 3x plus 2y is less than or equal to 6. Right? That's a constraint on x and y. Similarly, 1x plus 4y is less than or equal to 8. Because you only have 8 units of milk, so you can't make more than that. And what do you want to maximize? You want to maximize the number of drinks that you make, which is just x plus y. Right? So you want to maximize x plus y subject to 3x plus 2y less than 6 and x plus 4y less than 8. Okay, you have two constraints, two variables, two inequalities on two variables, and you want to maximize this linear objective function. So that's a linear program. So you can see that it's a very expressive framework. Right now, if I had, let's say, labor, a limited amount of labor, that would be another constraint. If I had a new kind of drink, that would be another variable. So you can see that by using lots of variables and constraints, you can encode lots of real problems, lots of problems as linear programs. Okay? So let's, for now, stick to this toy simple example. So, and let's try to see geometrically what the problem is. So I've written down the linear program there. I added in the other constraints explicitly. We know that the number of units of coffee, cappuccino and latte should be non-negative. So I said x greater than 0 and y greater than 0. But apart from that, I just copied the linear program that we have. Okay, so let's see. So this is the xy plane. And now I'm going to try to visualize this. Every point here is a candidate answer to this question. They might not satisfy the constraint, but it's a candidate answer. So this is the xy plane. Now, okay, let's see what these constraints tell us. So firstly, x is greater than 0, right? So let me see. So what does x greater than 0 mean? It just means that your point has to be to the right of the x-axis, right? It has to be on this side. It has to be on this side. It has to be on this side of the y-axis. This is x greater than 0. Okay? And similarly, y greater than 0 says this point is on the above the x-axis. Okay? So these two constraints are done. So let's look at the first non-trivial constraint. So 3x plus 2y less than 6. How does this look like? Well, if you look at 3x plus 2y equal to 6, so let's look at 3x plus 2y equal to 6. This gives you a line on the plane. So I'm going to draw that line. So I'm going to draw this. Actually, I should draw this line. Extend this out. Okay, it's not straight enough, but it's okay. So this is the line 3x plus 2y equal to 6. So along this line, for every point x and y, 3x plus 2y is equal to 6. Okay? So what's happening to 3x plus 2y on either sides of the line? Well, to the right of the line, on this side, 3x plus 2y is actually more than 6. On the left of the line, 3x plus 2y is less than 6. So that's something to remember. If you have a linear constraint on the plane, it will give you a line, and it will ask you to stay on one side of the line. So 3x plus 2y is less than 6 is asking us to stay to the left of this line. So 3x plus 2y less than 6 says you have to stay on this side of the line. Okay? More generally, if you're in 3 dimensions, if you have a constraint on 3 variables, linear constraint on 3 variables, that gives you a plane. And the constraint that x plus y plus z is less than 7 or whatever, a constraint like that, is saying that you should stay on one side of that plane. Okay? And in any higher dimensions, of course, I can't have a picture, but the same constructs continue to hold. So in any n dimensions, a linear constraint on n variables defines a hyperplane, and saying that the summation ai xi is less than b, a linear constraint like that, is saying that you should stay on one side of that hyperplane. Okay? It's called a half space. Okay, so 3x plus 2y less than 6 says we should stay on this side. So let me just... Oops. So far, we have to stay... So far, we are allowed this triangle. This is what we are allowed to venture into, because we have to stay on this side of 3x plus 2y and on the other side of x and y axis. Okay? So now let's look at the final constraint. X plus 4y less than 8. Again, this defines a line, and I'm just going to draw the line. All right, so I'm going to draw this line. Yeah. Okay. So this is the line x plus 4y less than or equal to 8. And the constraint x plus 5, it's the line x plus 4y equal to 8. And the constraint that it's less than or equal to that 8 is saying that we should stay under this line. Okay? So finally, we are just left with the space where we are allowed to venture into is just given by this region. Okay? So any point in this region, any point here satisfies all constraints. And so any point there is something feasible. You can actually make x units of cappuccino and y units of latte any point there. What we care about is the optimal one, which is the maximum number of drinks, but any point there is feasible. In particular, for instance, 0, 0 is feasible because you could make 0 units of coffee and 0 units of cappuccino and 0 units of latte using the resources that you have. So all the points in that region are feasible. And so this is, the word, I guess the key word to remember is feasible, meaning you satisfy all the constraints, and feasible region, By feasible region, we mean the, informally, it's the range of variables, not the range, I should say, the set of assignments to the variables that satisfy all the constraints. It's the region where feasibility is true. Okay. This is just some terminology that we'll use. Okay, that's good. So that's the feasible region. But the feasible region is pretty nice. It's not some crazy set. It's actually a quadrilateral here. And in fact, this will be an important fact for us. I guess I'll put in 3 facts maybe today. Fact 1, the feasible region of a linear program if it's non-empty is a convex polygon in 2 dimensions, but in higher dimensions you'd call it polyhedron. Okay? A feasible region of a linear program is a convex polyhedron. Okay? So polyhedron is, let's think of 2 dimensions for now, just a polygon, right? And the key word here is convex. Okay? Let me just define what convex is. So this is what convex is. A convex is a set of points is convex if you take any pair of points in the set, the line joining them is also part of the set. Okay? So a hollow shell is not convex because if I take 2 points in a hollow shell, the line joining them goes through the interior, and so it's not part of the set. Right? So if I look at these sets, this set is convex, right? It's a disk. So if I take any pair of points here, A and B, then the line joining them is also inside the set. So it's a convex set. Is this set convex? Is the set 2 convex? No? Yes? No. Okay, yes, it is no. Because clearly it has a hole here, right? So if I take A and B, 2 points here, and I look at the line, it has to go outside the set. So it's not a convex set. So you can't have holes like that. So this is not a convex set. Similarly, the third one is also not convex set because if I look at 2 points here and here, A and B, then I look at the line joining them, it goes outside the set. Okay? A set of points is convex if every line joining every pair of them is inside the set. Okay? So when you look at the feasible region of a linear program, you'll get a polygon that is convex or a polyhedron that is convex. And this is important because in general, minimizing convex functions on convex sets is easy. And that's the reason why linear programming is easy. Right? But that's not... but it's just important to remember that you're going to get a polygon which is convex. It's not going to have any holes, and in particular, not just holes, it can't even have troughs like this. So this is a trough. I mean, I don't know what's the right word. This is a trough. I'm calling this a trough. Right? Not going to have troughs like this. Everything will look outward pointing. Right? You won't have vertices that are inward pointing. Okay, so that's good. Okay, so now right, so this is, I guess, I would say the fact to remember. Okay, all right, so let's go back to our feasible set. Okay, it's a convex set. That's good. All right, so now recall what our objective was. Our objective is to maximize x plus y. Okay? So where on this quadrilateral is x plus y maximized? So how do we see that? Well, let's just try to make one drink. Okay? Let's say what is x plus y equal to 1? If I look at x plus y equal to 1, that is given by this line. this is x plus y is 1. Okay? So in particular, if I want to make just one drink, or in total one drink, I could pick any point in this feasible region here, which intersects x plus y equal to 1, and that gives me a way to make one drink. Okay, now I want to make more drinks. So which means that I need to increase the value of x plus y, right? My goal is to maximize x plus y while staying inside this feasible region. That's my goal. Okay? So is there a point with higher value of x plus y? Well, I can move this line. I can shift this line further and further away. I'll get new points. Like, for instance, if I draw the line x plus y equal to 2, okay? If I draw the line x plus y equal to 2, that's 2 drinks. And you see that it's still possible to make 2 drinks. In fact, you could make either 2, 0, or 0, 2, or 1, 1. This entire line is still feasible. It's doable. Right? You have enough resources to do it. Okay, you can make 2 drinks. Can you push it further? Can you make slightly more? Well, it looks like you can, because it seems like you can shift this line further. You can still stay inside the feasible region. In particular, like sort of the best you can do is to sort of look at this line here. Right? This is x plus y is 2.25. Okay? If I look at x plus y is 2.6. If I look at x plus y is 2.6, it actually is still feasible at this corner. And that is, in fact, the optimal solution. Okay? We're just playing around with how the linear program looks to infer properties of what's true about these things. And, I mean, there are many ways to arrive at the same fact. The fact that I want to arrive at is that the optimum of a linear program occurs at one of the corners of the polytope. Okay? Personally, actually, I don't like this geometric way of pushing the line, because it's somehow counterintuitive to me. I have a different way of thinking about it, which is, I guess we don't have time to, but maybe I'll post on Piazza on that. But basically, the fact that you want to arrive at, you could arrive at it in many ways. You could prove it in many ways. You can arrive at it in many ways. Is the following fact you should remember is the optima of a linear program is at the vertex of the polyhedron. I should say occurs at the polygon or polyhedron. Note that I'm not saying that every optimum is at the corner, but there are optimal solutions which are at the corners of the polyhedron. Okay? So these are 2 facts. Your feasible region is going to be like a polygon or a polyhedron, and the optimum of your feasible region of your solution will be at one of the corners. Okay? So a brute force approach would be to go through every corner of the polygon and see which of them gives you the largest value. Right? So in this case, you could go through all the 4 corners of this quadrilateral, and if you first figure out the feasible region, which is this quadrilateral or the polygon, and you go through every corner of this quadrilateral, and one of them is the optimal solution. Okay? So that's a brute force approach. But it's better than what we had earlier, right? So you should recall that when I wrote the original problem with real numbers, we didn't even have a finite time algorithm, because it's a problem of real numbers. But at least now I'm giving you a finite time algorithm. Just go through every corner, which is a finite list, and then the one which is which gives the largest value, is the optimal solution. Okay? All right, so that's two facts, I guess. Okay, now, okay, that's good. So we want to look for the optima at the corners, but then the question is, how do I compute these corners? How do I access these corners of the polytope? Right? How do I access the corners of the polytope? Well, note that the corners of the polytope are the places where these constraints meet. Right? In each of the corners of the polytope are places where your original constraints meet. So, if you are working in 2 dimensions, if you have 2 linear constraints, it's there in point of intersection. You can compute it easily because you have 2 equations in 2 variables. And by the same applies in higher dimensions. If you have an n-dimensional problem, if you look at if I give you n different constraints, linear equality constraints, if I give you n equations in n variables, by solving them, you can find the unique point of intersection if they're in non-degenerate position. So, in particular, this is, I guess, the sort of the third fact, which is also important, is the corner or the vertex of the polygon is given by the intersection or is the unique point of intersection of the constraints, equality of the constraints. Constraints of the hyperplanes that define the constraints. So for instance, over here, how do I find this point? Well, that point is given by solving, well, it should be on the line 3x plus 2y equal to 6. Right? It should be on the line 3x plus 2y equal to 6 and on the line x plus 4y equal to 8. Right? It's the intersection of those 2 lines. Now you got 2 equations in 2 variables, so you can solve for them and you can find the point of intersection. Okay? So if I give you m constraints in n variables, you can, how do you list every corner of your feasible region? Well, you just pick every subset of n of them, make them into equations, solve the system. You'll get one corner. Right? You have, if I give you m constraints in n variables, you'd need m choose n different corners that you can produce this way, and you just go through them and pick the one which is best. That gives you an algorithm. It's not efficient yet, but it's an algorithm. Okay? Okay, so the one last thing I want to do is to show you a small magic trick, I guess. So I said that the optimal value is 2.6. And I showed you these pictures and everything. Now, if you ask me, can you, if you don't trust me, and if you say, can you prove that the optimum value is 2.6? How can I prove that optimum value is 2.6? Well, I'll say, take this constraint, multiply it by 0.3, take this constraint, multiply it by 0.1, and then add them, 0 times this constraint, 0 times this constraint, just add them. So there's inequalities, I'm saying take the first constraint multiplied by 0.3, take the second constraint multiplied by 0.1, and add them. What do you get? You'll get x plus y is smaller than 2.6. So that's a proof that the optimal solution for this can never be more than 2.6. So I can prove to you that the optimal solution is never more than 2.6 by doing this. It's a magic trick, right? I mean, how did I do it? Well, I didn't pick the numbers very carefully. You can always do this. Whenever you have a linear program, you can actually prove the optimum is the right answer by adding the constraints. And that's part of the reason why linear programming is actually solvable in polynomial time. It's called this phenomenon of duality. We'll learn a lot about it in the class. We'll stop now.